All right, we're live. Hello, hello, Palash. Let me know if sound volume is not right, or if the background music is too loud or not loud enough. All good. All right, awesome. All right, cool. So today, let me. How can I? Well, it's been a while that I done a stream. So I'll share my screen. Hello, hello, Nicholas. Welcome back. So today we're going to be looking at XZ compression, and this was kind of prompted by a new component that we have developed at Polar Signals that basically scrapes any sort of Linux package repository, and it then extracts all of the debug info, so the information that we need for translating memory addresses to function names, file names, line numbers, and so on in Polar Signals, or generally for any profiling tool. And we essentially scrape all of these and then upload them to Polar Signals so that we can work with these and ultimately resolve symbols. And after implementing this component, it was pretty clear that this component one, of course, is using a bunch of CPU, and that's okay. Compression tends to be a CPU-bound operation, so it's okay that this ends up taking some CPU. But since this was a new component and we didn't really know all that much about it, other than using this library, it worked perfectly on first try. But we wanted to see whether there's some optimization potential here. For a little bit more context, so XZ compression, we can already see it kind of in the stack traces, and let me make these a little bit larger. We can already see it in the stack traces. It's an LZMA family compression algorithm, and so basically, since this is a file compression algorithm, it's of course a lossless compression algorithm. Let's maybe very quickly go over here, look at so this is the Wikipedia article, XZ, a lossless data compression file format based on the LZMA algorithm. So this is the same kind of algorithm that is used by 7-Zip. So this is a pretty awesome compression algorithm, and as we can see, it's definitely using quite a bit of CPU. And what's promising, I have no idea if it'll work today, but what is promising is that we can see several frames that where the leaf is taking some CPU time, right? So we're seeing it in this one, in the read op frame. We can definitely see it. We can see it in the decode frame, definitely, and in the decode bit frame. So hopefully by looking at, and here we've got read, other reads, kind of, yeah, so basically just reading. But hopefully that means that we can optimize some of these operations today. Like always, I, other than, creating this PeopleOfMe share from our production profiling data, I did not have a look at any of this code, so we'll be exploring it together today, and then hopefully, fingers crossed, we'll actually find some optimizations. All right, as always, feel free to keep the chat lively. Let me switch back over here. Sorry about that. I kept talking about the profiling data, but actually didn't switch back. But like I said, feel free to keep the chat lively. If you have any questions, any thoughts, comments, feel free to drop them in there. All right, so without further ado, let's then dive into the code. And let me actually share my whole screen. Here we go. All right, so like I said, I have already cloned the repository, but other than that, I haven't done anything. And looking at this code, I guess since basically the whole operation, the whole decompression operation is what we're going to be looking at, I think we should do a pretty high level benchmark. Maybe there is already a benchmark. Let's see. Looks like we've got a benchmark reader already. Let's see. Okay. Okay. I mean, I would say let's run this and we can see what we end up with. Our good old trick. What is it? Duck. All right, so we can decompress about 30 megabytes per second. I have actually no idea if this is representative for this type of compression algorithm. With typing. Hello, Matthias. Oh, yeah, actually, I forgot about this one. Today we're on Twitch for the very first time as well. So we're trying out some other platforms. So we've got a mixed chat here. Let's see if I can blend this in. Actually, I can. Now I wonder. Let me know in chat if this is more distracting than useful, because I think it's taking up some of the screen real estate. But maybe we can try this blending in this chat. Don't use this? Okay. I'll turn it off. I'll then try to make sure to look at the chat and then pull up any messages. Actually, Matthias, if you want to hop on the stream, you could. Tor actually couldn't end up making it today, so yeah, I could still. Yeah, I was trying that, but it doesn't look like I can make the chat overlay smaller. Might need to play around with that another time. Okay. No worries, Matthias. Nicholas just had a suggestion to reduce the sidebar chat if it's possible, but unfortunately it looks like Restream doesn't allow me to do that. But we're still learning. We'll figure it out. In the meantime, our benchmark did run through. So, I forgot to, classic, I forgot to actually take a CPU profile so that we can then see the whether the profiling data looks the same as what we were seeing in production. Otherwise, we might. I do have a representative file that we could use for a benchmark. Otherwise, Palash was suggesting we could try using a chat bridge for the next stream, so we don't have to use 2 chat windows. So I don't actually have to use 2 chat windows. I can see a single one, but I don't think, or you tell me, I don't know how your experience looks like, of course. Can you see the comments from Twitch, from Matthias, for example, as well on YouTube and vice versa? That'd be interesting to know for me. All right, so we've got our benchmark. Now, is this opened in another tab? Palash was saying in chat that we can't see Twitch messages. Yeah, that's what I expected, but maybe Restream cleverly solved this somehow. All right, so looks like this is doing both a write and a read. So we would only want to look at this one. Okay, so it looks like this is not quite the same workload as our workload. So I think what we're gonna want to do is write a new benchmark that is representative with our workload. Matthias was saying in chat, no, we need the chat overlay in Restream opening, just like I did, is good though. But then it uses up a bunch of space, and it doesn't look like it's Restream allows me to edit the size. So I'm not sure what the right thing to do here is. I see. Okay, sorry. Matthias was saying, yeah, then we'll just do the pop-ups like we've always done. Makes sense. Okay, so now let's go back to our benchmark then. So let's write a new benchmark then. Benchmark our workload. So we need our file. Okay, we already have a test data directory. That's good. And I have this data.exe, and I'll move that to test data for now. All right, we've got that. So we can open our file, data.exe. We want to set bytes to this. This probably, yeah. right? So that we'll see the megabytes per second that we are able to decompress. And now, all right, yeah, we want to record dialogues. That's a good thing to do. Now, yes, we want to seek to the beginning. We create a new reader. Then we copy to discard. This looks pretty good. Now let's try running this benchmark. We'll just only run this one benchmark. Oh, invalid. Magic byte. Actually, I know what's going on. The file is not. It's first an archive. What is? It's a regular archive, and I think it's files. As we said, this is a Debian package basically. So the thing that's really large here is what's in the data.tar.exe. So as we can see, this is 370 megabytes or so large. So let's try this again. What did I do now? Data.tar. Hang on. That was weird. Does anybody see anything obvious? Actually, one thing that I kind of want to do is just to remove any disk operations for the moment. I'm going to just read this whole thing into memory instead. Now, and this needs to be an X64. Now, please test in a bytes reader. Okay. Now, hopefully. Let's add a timeout to see where it's hanging. Okay, that was odd. But we can see 18 megabytes per second only. So, all right, now let's maybe do count 2. Okay, we'll have to survive this once. CPU profile, cpu.prof, old.txt. It's interesting. Yeah, so Matthias suggested to maybe add some logging to introspect. What actually surprises me is that it didn't show us any of this like metadata. I feel maybe I'm misremembering, but like I would have expected this to kind of show up pretty quickly. Anyway, hopefully we can make it fast enough that we don't need to wait for any of this. But we can see there are plenty of allocations happening. So that's definitely something that we can also have a look at. We'll start with the CPU profiling data, but this suggests we probably want to we probably also want to look at memory profiling data. Yeah, I think this is our major motivation today. We want to make things faster so that our benchmarking output is faster. Good problems to have, I guess. But now we should be close to having our data. Okay, so now, why does this keep opening on a different? Oh, okay, well that looks very, very much like the production profiling data that we grabbed. So this was, again, recapping, this is what we grabbed from our production workload, and this is with our like artificial benchmark, but this now looks very, very much like our production data. So that's good. Now we can actually work towards improving our specific workload. This kind of thing is pretty important, right? We saw that there was already a benchmark, but it was clearly not very representative of how we happen to use this library. And so that seems promising, that we can maybe improve things here that maybe people haven't caught necessarily with this default benchmark. I am going to do one thing because I'm pretty sure we're going to want to see memory profiling data as well. So I'm going to just run this again, but we don't have to wait for it this time. So all right. So again, I think the first things that we're going to want to look at are the things that have very large leaves. So I think decode bit is probably the first one that we're going to look at. So range codec.go line 191. So range. Decode bit. Okay. And this calls out to increase, bound. Let's see if we can see any of this. We can see decrease, we can see increase, but these are very, very small. Update code, LZMA prop bound. So this we probably want to have a look at not just this, but what we're going to want to do is we're going to want to look at the line information. I think it's going to be interesting here. Oh, today everything wants to open on my other screen. I don't know why that's happening. Okay, so here we go. So we were searching for decode bit. Okay, that's already here. So it looks like most of the time is spent doing this. There's also a fair amount in this if statement, which suggests if we could reduce branches, that could be interesting as well. So, I mean, pretty clearly we need to understand what this does. So we want to understand what p.bound does. Okay. And this uses about 1.5 seconds. I think it might actually be interesting to see if this is being inlined. So, what does this mean? Decode bit decodes a single bit. The bit will be returned at the least significant position. All other bits will be 0. The probability value will be updated. So what are we doing? If bound is larger than code, we set the range to bound and increase. And increase is what? This is the probability. Oh. This probably, okay. I want to look at memory profiling data for this, because this looks to me like it's all happening on the heap. that. So it seems like it can't find that. Let's look at this then. Okay, so read file is what uses the most. Okay, read up. That's interesting. We definitely saw this as well. Did we not? Yeah, over here. Okay. It's not huge, but it's definitely something. It's quite likely that this bit back here is this allocation. Looks like it's gonna be a tough one today. I think it's happening. So Palash was asking, how did I deduce that this is happening on the heap? So I think it has to be because P is a pointer, right? So this is always, anything with a pointer is always gonna be allocated on heap. So this strikes me that, you know, all of that is going to be modified on the heap, which is much more expensive than doing these operations on the stack. So let's maybe walk up a little bit and see what decode does. So this is literal codec and literal codec.go line 97. Okay, so I would expect to see this probably do an allocation here. Or maybe even allocate this entire slice on heap. So decode bit is what we're going to be looking for now. That. Okay, so we didn't find it here, but let's check the CPU profiling data there. Oh. No, sorry, we're just looking for decode. So it's pretty. So here we can see the same thing that we're seeing in the Icicle graph. Yeah, I think I want to try not passing in a pointer here, but instead passing passing the direct value. Let's see if we can make that work. It's probably, the code is probably going to look quite a bit more messy doing this. So this doesn't modify anything, that's good. Then we want to, okay, so let's do this. And then we return key in, out, ability. I guess we can do this. We can do this. But ink this returns. So this is plus equals, so we do p plus this. I'm not 100% sure what the operator precedence here is, so I'm just gonna go with this. And it returns prop, and then do the same here. P minus this, return prop. We need to return. Matthias is saying pprof always does weird things when opening. Yeah, it's one of those things. We are working on getting all of this into pprof.me and Polar Signals as well, so that we no longer have to do any of this. Anyway, so let's let's do p out equals p here, and then we do all of our operations on this. Can you? I don't think I've ever done this, but can you do this? Yeah, no, it's really clear. That's what I thought. Oops. So p out equals p. P out that, then p out equals this, p out this. Now it strikes me as odd. Why even do this at all? The named return values don't make sense here. They never do any of that. Everything's explicitly declared. We even do this, and then this is not necessary. I need to do this, we just do this. Yeah, Palash was saying that named returns break brains. I definitely agree. I think there are very, very rare cases where they truly make sense, and maybe I don't see it yet, but it doesn't seem to make sense to me here. All right. So we've done something. Let's run our benchmark. We'll not necessarily aim for significance just yet. Matthias is saying named returns shouldn't exist. I don't know if I necessarily would go that far, but I think they're definitely a very, very tricky thing. Assignment mismatch. Okay, yeah, we need to in what was it? LZMA, literal codec, probs, I. Making sure that we're doing everything correctly. Some more conversation on named returns. If named return weren't a thing, you could still do var error at the top and get the same. You're probably right. I don't think you're missing anything, Matthias. All right, let's now see. Okay, there's still more. Prob 30 invalid operation cannot indirect p variable of type prop. All right. What did we do? Matthias was saying, all right, it's time to break Go 1. Hello, hello. Welcome to Let's Profile. Welcome. Let us know in chat if you have any questions. Awesome. Looks like you've maybe watched a couple of episodes before, but not live. So welcome to a live episode. Let us know if you want to see anything specific. Maybe just recapping what we're looking at today is this workload that uses happens to have to work with files that use this XZ compression algorithm. And we saw that it's using quite a bit of CPU time. This is an algorithm that we have to use for a specific workload in polar signals. Actually, and then we found that the benchmarking data in the repository is not exactly matching our workload. So we created a new one, and we could then see pretty much exactly the same in our benchmark as we were seeing on production. So now we're kind of digging through, and we think we found something where something's being done on the heap that we don't think is necessary. We think we can get it to be on stack, and hopefully that'll be a much faster way of doing things. All right, prop 52. What is that one? Decode bit. Okay, looks like to remove these. Yes, awesome. You're on Twitch. We're actually on Twitch for the very first time today. Glad you could catch us. All right, so, okay, this might get more hairy than I thought. So what's happening here is that the pointer to prob is being passed and then modified in encode bit. Let's see. So Not sure if this will actually work, if I'm honest. But we might try it. Return variables. What? Too many return values. Decode bit. Okay, I think it should be okay. I think we should be okay if we return P in all instances. So range encoder. And the modified hub. So question chat was, can you find out what's allocated to stack versus heap, for example, in profiling data? So I think in profiling data, we actually don't see it directly. We could, if we actually had this data now, we could actually see if we can see that here. This is the production data, but it doesn't look like we can see. No, it doesn't look like we can see this. We would want to see essentially the kinds of memory accesses that are happening. That's not something that we can see here. We could see it by enabling some compiler flags. It would tell us whether something escapes to the heap or not. But in this case, it's actually quite obvious that it has to be on the heap, because probability, the prob here was a pointer. Anything that's a pointer has to go onto the heap. Whereas anything that's just a value in Go tries as much as possible to stay on the stack typically. So that's just what we're trying to do right now. All right. Here we have the return named returns again. Oh my, okay. Looks like we're gonna be working our way through the whole library. Encoder 88. What are these? What kind of decoder is this? No. Okay, so is match gives us the, okay, this is the probability, so we need to set it here again. So b.state.is match 2, and we want to make sure we already have an error. That's the challenge. We'll see. We'll see if we manage to optimize this today. Like I always say, we we try our best, but we don't look at the code beforehand. So there is bound to be an episode one day where we fail, and that's okay. That's sometimes happens when doing performance work. So. All of these are always, yeah. Not use state value of prop. This is a probability states. Whoops. I should better just copy this. Hopefully this won't stay too mechanical for too long, but that might happen. And maybe we're doing something that can't work at all. We will find out. Now we want to go to encoder. Correct. Okay. I think we're good, but to be honest, this is probably the episode that I feel most unsure about so far, because I don't think I very deeply understand the compression algorithm. We'll see. Wanted to blend this in one more time. Would not want to try optimizing code that I do not understand. Hopefully, this show can show people that even, or especially if we manage to do this type of thing in code bases we are not familiar with, then you should be able to use these same methodologies with code that you are familiar with. To have a large impact. Matthias is saying that's often how you can find the most impact, though. I think it really strongly depends on the particular situation. I think there are cases where you run one very specific workload a lot in your company, then it's quite likely that there are lots of cases where you can optimize just by optimizing code that you're very familiar with. Looks like at some point they did stop using named returns in this code base. Slowly but surely migrating to what Matthias was saying about putting the var error at the top instead and getting kind of the same result. All right, I think we're slowly but surely getting there. very soothing to have some mechanical work, actually. Hopefully my keyboard is providing some ASMR. All right, now we're going on to the next codec. So now we're gonna go to the length codec. I'll be honest, if this avenue is not working, we're probably not gonna be able to find anything in time today. We're already 1 hour into this. Let's see, what do we have here? Choice is probability. All right, so we set but hopefully this is all very mechanical, and since these are all values, I think this should ultimately work, but we'll see. Congratulations. Even if it's unrelated to the stream, you got your first PR merge into Prometheus, which is that's awesome. Any contribution is important and ultimately contributes to the longevity of the project. So thanks for the contribution. I'm glad I switched to copying instead of what's happening here? What's this? Okay, this is something else. All right, so length codec. Now we're going back to some somewhat familiar territory. All right, what do we got here? Okay, we need to make sure that this is that. Actually, this is code that we already looked at today. Okay. I think we're getting towards the end. This, okay, great. So we're gonna be itc.props. No. And Here we do the same thing again. Whoops. Something. Okay. DC props and hopefully we're not messing with the maintainer's style by removing these, but hopefully we're making it a little bit easier to reason about. Okay, so we can do 81. Whew. All right, I think we are almost there. Thanks for bearing with me. More of these V. E is U and we gotta need V as well. All right. Okay. Something's happening. Running our benchmark. Oh no, I don't think that did anything. If anything, we might have made it worse. That's interesting. Why is that? It might still escape to heap, of course. Let's look at the new profiling data then. So, still in decode bit. Let's have a look at these then. Let's see. I didn't save something maybe. No, it doesn't look like it. I'll, just for good measure, I'll run this benchmark again, but I don't think that's what happened. Good catch though. Matthias is feeling with us and was saying maybe we didn't save the file. That'd be the nicest outcome now. So It looks like this if statement is really the problem, right? And I think we actually saw that before already. Maybe I kind of went down a rabbit hole that was unnecessary. But that happens. That's okay as well. So oh, I did not see that. Thanks for checking that. Not sure if you looked at this before I joined, but there is a PR open to inline decode bit. That is definitely pretty interesting. Let's have a look at that one. Looks like this was 3 weeks ago. Wow, this is all pretty recent actually. Very interesting. So it looks like they did a bunch of work to make sure decode bit can be inlined. Interesting. Looks like the same person opened another one. Looks like I should have looked at these pull requests before. I guess since we weren't particularly successful with our improvement, I'm still gonna save this just for good measure. Yes, that's exactly what I was thinking as well. Matthias is saying, let's try our benchmark with these changes. That's exactly what I was thinking as well. Oh wait, the reader test. That's where our benchmark is. So work in progress, remove infer from probability. All right. So we already, yeah, okay, so we're gonna be able to just add this person's Horizano. Horizano. Matthias was saying, at least recently you learned you don't need to add these remotes. Is that so? How would you pull from it then? You can simply do git pull HTTP Interesting. I had no idea either. Now we've already done it. So feed inline decode bit. Cool. We managed to take our benchmark with us. Matthias is saying such a life changer when pushing changes to a PR as a maintainer. Yeah, makes sense. All right, so yeah, this does look like it indeed has a pretty decent improvement. We need some more significance for this, but it does look good. So from 18 to 22 megabytes. And we've got some more comments in chat. Recently started using the GH CLI GHPR checkout for this, but vanilla Git sounds better. To be honest, I know a lot of folks who really love the GitHub CLI, so I think there's nothing wrong with using that either. Matthias is saying he uses Git GH2. It's great. I guess one lesson learned from today's episode is we should always check open pull requests before doing performance optimizations ourselves. Now let's do this. All right, so that's definitely pretty awesome. We've got a 25% increase even. So let's comment here. Just want to add, we just benchmarked this against our workload, and we even see a 25% improvement. Some work. Oh no. And let's see what they did here. The byte reader function in some cases creates a B reader that reads 1 byte at a time, resulting in inefficient performance. Yeah, we did see this as well in the profiling data. We could see it here. Whoops. Could see it over here. B reader, read byte, and then on limited reader calls that, and that ends up being very, very inefficient. That was one of the other avenues that we were thinking of earlier as well. So very cool that they already went down this route. I'd say let's give it a try as well. Avoid B reader. Looks like we did not achieve our goal of making this so much faster that our benchmarks are running very quickly. Actually, you know what? it could also be that just simply reading the like 400 megabytes file into memory is already pretty expensive to begin with. It might be that. But if I'm seeing these numbers, I don't think we are going to be seeing a huge improvement here. I think that's kind of based on what we can see here as well. But we may see 10%-ish improvement as well. It's probably more like this one, like the 6% though, because the limited reader is what's basically going to be going away. What's opening over here? Okay, this is downloading stuff. Here we can see the AR command that we started with at the very beginning. And our good old read all. I guess it has to allocate at least memory to read it into. That's fine. All right. Yeah, looks like we're not really seeing any improvement with this one, but that's all right. It looks like they saw an improvement on their workload. All right. I guess the only thing that we can maybe do last for today is check out what the profiling data looks like on this branch, just in case if there's maybe something after these changes that we can quite clearly see. I somewhat doubt it, but we'll see. All right, so upload this. We can see tree, decode bits, read byte, limited read, counting read. Interesting. All right, tree, decode bits. That was the new function that the contributor added, so maybe there's something new. Tree decode matched, but tree decode bits. Let's check it out. Have a memory profile open, or what is this? I'm curious. Then mistype it or something? Tree decode bits. I don't know what happened there. So we can see that now a decent amount is spent in P.Inc. I guess we can try range decoder. We'll give this a last try. We'll try to rebase our changes on top of these. What did we call it again? Have this fancy custom git command. Show me the most recent. So git rebase feet inline decode bit. Okay, let's slash these. There's going to be some conflicts. Yeah, of course, this is gonna make sense. We're gonna do this one as well. Ow. I think this will be the last try for today. Let's see. Maybe we'll get lucky. Feeling rather pessimistic today, though, about this. We don't have our benchmark. Right match, distance out of range. I guess now we probably broke a test unintentionally. What did I just do? I individual tiles is not. Um. So, what did we actually modify now? So we're writing prob stack here, writing prob stack here. That's looking correct. What was the other one that we had config in? Config in literal codec. Props, symbol. Interesting. Interesting that we managed to get it to work before, but not after those changes. Let's just make sure that there's not something in here. Or copy error. Right match distance out of range. Distance out of range. Here we go. RDMA decoder. Is that the only distance out of range? Interesting. All right. I mean, I think today I'm at the end of my foo. I think now it would require diving much deeper into this algorithm to understand what's going wrong now. Is there anything else that this person edited? We've got a suggestion in chat, add an error. Should get some info how it reaches it. Let's try that. Here. Yes. So we go there. Decoder dict. Decoder 186. match. All right, so that must mean 2, 1, 2, 2, 2. By operation. Oh, you know what? We did at the beginning read something about read up. It's the state that we kept modifying. Let's go. So 2, 2, set 1. Decompress. Yeah, I mean, this is the highest level one, basically. Go into from reader 2, but I guess this is just my number 141. Yeah, this is just this. You're probably this reader goes. This of course. Yeah. What did this change? That we previously had. So this did we add returning the probability from tree decode matched byte? Aha. This might be the issue. So range codec. tree code. And where is this used again? By tree decode bits. Wait, so I'm seeing some. So we have PS. Then we get our bounds again, but we actually need to do this. Is there any other code that was doing something like this? There was also something about reverse something. Okay, okay. Okay. And not only that, but we actually need to ensure that at this stage, yes, we write it back to this slice. No. Okay, looks like we've got this a couple of times. We read this, we do p equal this, and we again write this back, and hopefully p equals this, p equals this. Oh, yeah. Okay. Got closer, I think, but no dice. Let's look more of this patch. Had another comment in chat from Egon. Also a side note, if you keep the pointer to the slice location, you can avoid a bounce check when writing back the value. Not sure whether it makes a difference in this case. Yeah, I think this is ultimately what so the thing that we were trying to do is from the very start, we think there is a there's some work happening on the heap that we would like to prevent, but it could be that we may be actually adding other work like bounce check potentially that ultimately ends up creating more work again. I'm not sure. I suppose the bounce check could be eliminated though by having accessed it before. Tree decode matched byte. Did we do this one? Oh, we did. And decode it. Still contains this as well, yeah. Just make sure that we're... Oh, actually we have it. I was so quick at glancing over that this is a panic that I didn't realize this is a different panic. So we've got range codec 269. Oh wow, this is... Oh. Symbol is changing here. I definitely overlooked this. Yeah. Now, yeah, we're doing this everywhere basically. Egon also spotted it in chat. Symbol has been modified, yeah. I patched that earlier. Yeah, we need to do it here as well. Offset changes while offset doesn't change. Does bit change? Not yet. Wait, no, offset does change. Okay, so symbol before and offset before. Okay. Maybe this was it now. All right. We may have something. $23 megabytes per second. Actually, I think we made it worse. Shame. We go up. This was in the other tab. Maybe we did make it faster. Let's compare then. A couple of times. I think I might have thought about the 25% earlier instead of the amount. Earlier we saw a 25% improvement with this patch at first, and now, and I think we might have had something around along the lines of 22 megabytes per second. All right, so let's first compare it. So we see a 28. Okay, so let's rename this to new no pointer, and we'll add this. Go back to we don't have our benchmark. So that's our benchmark. All right, 22 megabytes, and we saw 23 something. That looks promising. Might have not been the biggest performance improvement we've created on this channel, but you know, we'll take anything. But that looks pretty consistent. So it looks like we improved by maybe 5% or something along those lines. All right, so the first improvement we've got, we can do 22.8 megabytes per second. The total improvement today is we can go up to 23 megabytes, 23.4 megabytes per second. And the improvement between the open pull request and this one is, it's not huge. we've made it about 3% better. But we at least we did make it faster. So there was definitely a time today when I didn't think that was necessarily going to happen. I guess our most recent profiling data I destroyed again with the I'll just reset. Just running this once again, just so we can see the profiling data again. But I suspect that we've removed probably that CPU time that we were seeing at the increase level. Yeah, looks like there was a minor improvement here, but it's not very large. But yeah, nevertheless, we made some improvement today. Sadly, it wasn't as large of an improvement as we maybe have hoped. But in total, we have, what did we say? In total, we did manage to get a 28.5% improvement. So thanks to this open source main contributor, we actually managed to still turn this episode around. So yeah, definitely one of the tougher episodes today. As always, if you have any suggestions of something that we should profile and attempt to optimize, or if you want to come onto the show and you have maybe the Parka open source project deployed so that we can look at data together, we can do that. I think it's always best if we have profiling data from real production systems. Just to kind of go back, this is this workload that we started out with. This is a workload that basically scrapes Debian repositories for their content, and Debian packages happen to be compressed using this compression algorithm, and that's what led us down this path. So we always love to do performance optimizations on things that are real, right? Like this is a real workload that we happen to run at Polar Signals. So if you have any workload that you would like to attempt to optimize, we can definitely do that together here on the channel. But yeah, otherwise, drop your suggestions for what we should optimize next in the chat on Twitter. Definitely give this video a like, maybe a subscribe. And then hopefully we'll see you next time. Thanks for the awesome chat today. We had a very lively chat, some new faces. That's always exciting to see. So yeah, hopefully everybody had a nice end of their Friday with this episode live, and hopefully everyone catching the recording also learned a thing or two. With that, we're done for today, and see you next time. Bye-bye.